So for problem number 9, we're trying to prove these statements here about sets A, B, and C. So for item A, this is an if and only if statement. So we're going to break this down into two parts. So part one, we are going to say assume A is a subset of B, right? And then we have to show that this thing here follows. But we're going to work this by contradiction. So we're going to say let A minus B not be empty, right? We're going to assume the opposite and then show that it leads to some contradiction. Then there exists some x such that x belongs to A and x does not belong to B. But A is a subset of B. So if x belongs to A, x has to belong to B because A is inside B, right? So x belongs to B, which is a contradiction. And so our conclusion should be, therefore, A minus B has to be empty, because we suppose that it wasn't empty, right? That there was some x in that set, and we showed that that led to a contradiction. So now we're going to do part 2. So for part 2, we're going to assume that A minus B is empty, and then show that it leads to A being a subset of B. So, assume that A minus B is empty. Then, I'm going to begin a different way. I'm going to say, let X belong to A. Note that A minus B is empty, so X has to belong to B, right? Because if I remove all the elements of B from A if it's empty, it means that X belongs to B. Thus, A is a subset of B. So fairly straightforward, this part. So we have shown both part, right? We should have shown that the left-hand side leads to the right-hand side and vice versa. So we have proved the biconditional. So for item B, we are assuming that if A is a subset of B union C and A intersection B is empty, then A is a subset of C. So for B, we're going to let A be a subset of B union C and A intersection B be empty, right? So let X belong to A. So we're beginning with let X belong to A because we want to show that, hey, if it is in A, it must be in C, because that's what we're trying to show. Let X be in A. Then X belongs to B union C, right? Because A is a subset of B union C. So X belongs to B, or X belongs to C. Note that A intersection B is empty. So if X belongs to A, actually maybe I'll write this a different way. Note that this, and I'm going to say, given that X belongs to A, then X cannot belong to B because the intersection there is empty, right? So thus, it must be the case that X belongs to C. And the reason that it must be the case is because up here we said that so X belongs to B or X belongs to C. So since it cannot belong to B, it has to belong to C, right? So we have shown here that, hey, we took some element in A and showed that that element was in C. So our conclusion is going to be, therefore, A is a subset of C. And that is it for item B. For item C, this is a biconditional once more, so we are going to do a two-part proof. Let me erase this. So for item C, we're doing two parts. So part 1, we're going to assume that this thing is true. So assume that C, oops, that's not what I meant to do. Assume that C is a subset of A intersection B, right? So, and we want to show that it leads to C being a subset of A and C being a subset of B. So we're going to say, let X belong to C. And actually, I should have put this here. Yeah. Note that C is a subset of A intersection B, so X belongs to A intersection B. Then X belongs to A, and since it is an intersection, it has to be in both, and X belongs to B. So we have that if X belongs to C, it is in A and it is in B. Thus, X belongs to C implies X belongs to A, and X belongs to C implies that X belongs to B. So C is a subset of A and C is a subset of B because it implies that it belongs to both, right? So that's it for part 1. And now we're going to do part 2. So for part 2, we're going to say part 2, assume that C is a subset of A and C is a subset of B. And so what we want to show here is that it leads to C being a subset of A intersection B. So we're going to say, let Y belong to C, right? So because C is a subset of A and C is a subset of B, then Y belongs to A and Y belongs to B. So Y belongs to A intersection B, because by definition, right? Because of this and. So we have shown here, hey, if C is a subset of A and C is a subset of B, then any element that is in C is both in A and B, so that element has to be in the intersection. So we're going to say, thus, C is a subset of A intersection B, right? So we have shown it both ways, and that is it for item C. So item D, we assume that A is a subset of B, and then show that it leads to A minus C being a subset of B minus C. So we're going to say here, for item D, we're going to assume or let A be a subset of B, right? And now we're going to say, let X be an element of A minus C. And we begin here because we want to show that, hey, if it is here, then it is there as well, right? That's what it means for it to be a subset. Let X belongs to A minus C. Then X belongs to A and X does not belong to C. because that's the definition of it belonging to A minus C. And then we're going to say, note that A is a subset of B, so X belongs to B and X does not belong to C. So if X belongs to B and X does not belong to C, then it means that thus X belongs to B minus C. It fits the definition, right? So we have shown that some element that is here must necessarily be there as well. So therefore our conclusion is A minus C is a subset of B minus C. That's it for item D. Now for item E, we want to show that both of these are equal. So we're going to do an if and only if sequence of claims. So for item E, we are going to begin with X belongs to A minus C minus B minus C. And I always begin with a more complicated one because I find that that's easier to think about, right? So we begin here, and then we want to do an if and only if chain of reasoning, and then end up here. So we're going to say X belongs to this if and only if X belongs to A minus C and X does not belong to B minus C, right? So now we're going to expand this, and we're going to say if and only if X belongs to A and X does not belong to C, right? If and only if X belongs to A and X does not belong to C. And if it is not the case that X belongs to B minus C, it means that X does not belong to B or X belongs to C. So, and X does not belong to B or X belongs to C, right? Because think about it. If this is B and this is C, right? So B minus C would be this section here. So if we're saying, hey, it is not in B minus C, so if it's not in this section, it either means that it is not in B, or it means that it is in C, right? Because if it is in C, then it is definitely not there in blue, and if it is not in B, so if it is outside here, then definitely not in that area in blue, right? So once we have said this, now we're just going to expand this, and we're going to say if and only if X belongs to A, right? And X does not belong to C, and X does not belong to B, or X belongs to C. So we have expanded this, and now let's think about what we want. We want that A minus B minus C, right? So we're just going to rearrange this. So we're going to say if and only if X belongs to A and X does not belong to B, right? And so we've rearranged this, and I'm going to put a parenthesis around it. And so we have and X does not belong to C or X belongs to C. So if X does not belong to C, right, that has to be guaranteed. We're saying and X does not belong to C. So we're going to say and X does not belong to C. And now we can just drop this or X belongs to C because we know that that's going to be false, right? If we need this and X belongs to C, the and means that this has to be true. So if that's true, this part here definitely isn't. So we can just ignore that because the or, it doesn't have to be true, right? If we have other true statements. So, and now we've just basically gotten to the definition. So now we can say if and only if X belongs to A and X does not belong to B means that if and only if X belongs to, I'm going to put here A minus B and X does not belong to C. And that's the same thing saying if and only if X belongs to A minus B minus C. And that is it for item E. Now let's do item F. So let me erase all this. And so for item F, we're supposing that A belongs to C and B belongs to C. And we want to show that this leads to A union B is a subset of C. So we're going to say for item F, let A be a subset of C and B be a subset of C. So now we're going to begin with A union B. So we're going to say let X belong to A union B. And the reason that we're beginning here is because we want to take some element in A union B and show that it belongs to C, right? So then this means that X belongs to A or X belongs to B. Note that A is a subset of C and B is A is a subset of C. So I'm just gonna I should continue, yeah. And B is a subset of C. So from here, we're going to have that, thus X belongs to C in the first case, right? Or if X belongs to B, then that means that X belongs to C because B is a subset of C, right? So if X belongs to A, because A is a subset of C, it means that X belongs to C. Or if X belongs to B, we have that B is a subset of C, so X belongs to C, right? That's the kind of causal way of thinking. Let me remove these. So in either case, X belongs to C. So we have shown that some element in A union B must be in C. And so our conclusion is, therefore, A union B is a subset of C. That's it for item F. And now for item G, this is going to be a little bit longer. So we're trying to prove that A union B intersection C is a subset of A union B intersection C. So for this one, let's see what we're going to begin. So we're going to say for G, let X belong to A union B intersection C, right? So let's just expand. We're first going to expand this intersection. So that means that then X belongs to A union B and X belongs to C. Now we're going to expand this here. So X belongs to A or X belongs to B and maybe I'll put this here, and X belongs to C, right? And so let's see what we're trying to prove. So now what I can do here is just move this parenthesis and just say, so X belongs to A, or X belongs to B, and X belongs to C, right? And so once I'm here, I can just put these parentheses and say, so X belongs to A, or X belongs to B and X belongs to C, just means that it belongs to the intersection of B and C, or X belongs to the intersection of B and C, right? And then lastly, we are going to join these with the or, so we're going to say X belongs to A union B intersection C, because the or is just the union, right? So that's it for item G. And now for last one, we want to show that A minus B and B are disjoint, right? So we're going to say here, let's see, we're going to say let Y belong to, I think we should, oh wait, let Y belong to A minus B, right? Then Y belongs to A and Y does not belong to B. Thus, A minus B is empty since Y belongs to A minus B and Y does not belong to B. So that is it. This one's fairly straightforward, and we are done with problem 9.